Very well. So now we formalize the informal argument of before, and we go through the formal proof of the source coding theorem. So, as usual, we use the approach of random coding, and in particular, for given epsilon greater than 0, we choose a conditional probability distribution of x hat given x, such that the following expectation of the distortion x hat is satisfied. Notice here we require distortion to be less than d divided by 1 plus epsilon. Okay, of course, there are distributions that satisfy this constraint. If they are not, it means that the set over which we are trying to optimize is empty, and therefore, this distortion is unachievable, and then we are done. So, of course, we assume that there are some distributions for which this is possible. Now, with this distribution, of course, we induce a joint probability distribution of x and x hat given simply by the product p x hat given x. And then we can marginalize with respect to x by summing over all x's and obtain the corresponding marginal probability distribution of x hat. So with this probability distribution of x hat, we generate 2 to the nr sequences of length n, and these form our quantization codebook. So this is the random quantization codebook that we generate in this way. And now we use the following encoding and decoding rules. The encoding function works as follows. Given a source sequence x, find the index m such that there exists a jointly typical code word x hat of m in the codebook. So in other words, this means look for all possible x hat 1, x hat 2 in our codebook. Let's call it Cn. This is Cn. As soon as we find one sequence that is jointly typical to our source sequence, then we consider, we pick that index m, and this is the index generated by the encoding function. For the decoder, given the index m, we simply output the corresponding code word. So it's the simplest possible thing. So this is, if you remember, in the proof of channel coding, we had a very simple encoder. Given the message m, transmit the code word x of m, and a very complicated decoder that output the index of the unique code word jointly typical with the output sequence y if such code word is found. Otherwise, it would just pick an arbitrary index, for example, index number 1, and output in index number 1, or declare an error. Here is the role is reversed. There is a joint typicality encoder that finds a code word in the codebook jointly typical with the source sequence and output the corresponding index, and the decoder is simply given the index, produce the corresponding code word as the representation point. Now we want to analyze the error probability for this encoder. So when the encoder makes an error, when it doesn't find any such sequence in the codebook jointly typical with the source sequence. So in other words, the error event is the event that a randomly generated source sequence is not jointly typical for all code words in the codebook. And then we can analyze the ensemble average probability of error by taking, basically by averaging over all randomly generated codebooks. And this means considering the probability that a randomly generated source sequence is not jointly typical with other sources generated with the marginal distribution of xn but independent of x, because you see the codes are generated independently of the specific x generated by the source. They have the correct marginal distribution p x hat, this one, but they are independent because they are generated beforehand. So the probability that such a source sequence is not jointly typical with those independently generated sequences x hat for all n. Now, if you remember, this probability is exactly what we have analyzed in the covering lemma. And we know that this probability goes to 0 provided that the set of generated code words is large enough, and in particular that the exponent r must be larger than the mutual information of x and x hat plus some small quantity delta of epsilon that is vanishing when epsilon vanishes. Okay, so here the fact that the encoder will not make a mistake and find at least one jointly typical code word with the source sequence is guaranteed by the covering lemma, subject to this condition, subject to the fact that the rate r is greater than the mutual information plus delta. At this point, we can analyze the achieved distortion by this scheme. So we consider the ensemble average distortion achieved by this randomly generated codebook with this joint typicality encoder. So this is the expectation of the distortion function applied to the source sequence and the corresponding selected code word. And now we have that we can divide this by conditioning on the error event and the complement of the error event. So we have here the probability of error times the conditional distortion given error, and then 1 minus the probability of error times the conditional distortion given no error. So what happens? In the case of error, the decoder picks whatever, any sequence, and therefore the distortion will be upper bounded by a d max. D max is a uniform upper bound to the distortion, and this exists when the distortion function is bounded. So there is, for every x and x hat, there is a maximum for which for any x hat, d x hat is less or equal than d max. So the proof is particularly simple when the distortion function is bounded. When it's not bounded, well, we have to work a little bit more. But when the distortion function is sufficiently well behaved, the proof still goes through with a little bit of more care. So we consider this case with this sort of upper bounded distortion. So now here, to analyze the other term, so the term in the case of no error, it means that subject to no error, it means that the sequence x and the sequence x hat are effectively jointly typical. And what happened to the empirical mean of two jointly typical sequences? Well, we know that this is always in between by the typical average lemma. We know that this 1 over n sum d xi hat, because the sequences x and x hat are jointly typical, this is always in between the true mean, which 1 minus epsilon, the true mean, but the true mean was, we chose the true mean, if you remember at the beginning, to satisfy this inequality. So we have here that this is in particular less or equal than 1 plus epsilon. So this is the true mean, true, and is true, but true is less or equal than d over 1 plus epsilon, so this is less or equal than d. So at the end, this term is less or equal than d. So since this part tend to 0 and this part tend to 1, and this 1 plus epsilon times this thing is less or equal than d, we conclude that these schemes achieve distortion d. So what we have proved that the pair of R and D is achievable provided that R is larger than the mutual information. So the proof now is completed by picking the conditional distribution that minimizes the mutual information subject to this constraint, and then letting epsilon go to 0. Okay, so we have proved that the rate R of D, which is the best possible rate for given distortion D, is less or equal than the mean of the mutual information over all possible p x hat x, such that the distortion is less or equal than d. Okay. Now, in order to show that this is in fact equal, we have to prove that you cannot do better than that. So we need to have a converse statement that says for rates less than this quantity, there are no codes achieving distortion D. And as usual, the proof is done in a slightly different way. We say, suppose that we have a sequence of codes of rate R achieving distortion D. I don't know how they are constructed. Then, through a sequence of information theoretic inequality, we conclude that then R must be greater or equal than this quantity. And this proves then the equality. It means that the upper bound and lower bound coincide. So in order to do the converse, we need a lemma, which is in fact very much similar to that lemma we have proved in the converse of the capacity cost function. If you remember, in the case of capacity cost function, we have proved that the function C of B as a function of the cost B is non-decreasing and concave. So it's something that looks like this. And it turns out that for the rate distortion function, R of D is non-increasing and convex. So it's something that looks like this. Okay? So this is this lemma that says that the rate distortion function is convex and non-increasing with D. The proof is very, very similar to what we have seen for the capacity cost function. In fact, follows exactly the same principles and is given here. I will not go through because it has really the same idea. Okay. So at this point, what we can do is, as I say, assume that we have a sequence of codes, Fn, Gn, of rate R, satisfying that the distortion is not larger than D. And then, through a sequence of inequality, we are going to conclude that in this case, then the rate must be greater or equal than R of D, which is exactly this maximum or this minimum of the mutual information between X and X hat. So we work as follows. We given the code and the random source sequence, then we can define the random variable M as the random index generated by the encoder in the presence of a random realization of the source sequence. Because the function f is fixed, so we can define M as f of n, f sub n of xn, which is of course a random variable. And then we define also the random vector x hat n as the reconstruction function applied to this random index. So basically, given the code and given the randomness of the source, so the realization of the source, this induces a distribution on the indices m and on the reconstruction points. At this point, we can write the following. The log of the size of the messages, which is nr, is certainly greater or equal than the entropy. In fact, they are equal if the messages are uniformly distributed, but we don't know how these messages are distributed because this depends on how the code is built, and we can only assume that there exists a code. We don't know how it is built. So in general, log of the size of a message set is always greater or equal than the entropy of the messages. Then we can subtract this quantity, right? And so we make this lower because entropy is non-negative. This difference of entropies is the mutual information. Now we use basically the data processing inequality, right? Because we have the source xn, the encoding m, and then we have x hat by the decoder. So the mutual information between here and here is greater or equal than the mutual information from here and here. So we get a lower bound by data processing. Then we use the chain rule with respect to the sequence x, right? And we get this expansion. At this point, we use the chain rule in reverse mode. So if we take any term here and we break it into simply xi and xi minus 1 plus xi and x hat n given xi minus 1, right? Then you see that the d's minus d's is equal to that, right? So we have this, but now we recognize that because the source is memoryless, the mutual information between xi and all the symbols from 1 to I minus 1 is 0, because memoryless means that symbols are independent. So this mutual information is 0. And at this point, we can simply neglect all the variables inside here but xi hat, and of course we get a lower bound, because when you throw away terms inside the arguments of the mutual information, you can only decrease the mutual information. That's easy to see again by the chain rule. So we get this lower bound. But now we know the following. We know that there is for every, so now we do not know what the joint distribution of these two variables are, because this is induced by the randomness of the source and the code that is given, okay? But this is the ith marginal distribution, for two symbols xi hat, and this ith marginal distribution induces a certain level of distortion that I can call di equal to this, okay? The distortion function applied to this pair of jointly distributed random variables, okay? Now I know that for any possible distribution xi hat, this mutual information is lower bounded by the minimum of the mutual information over all joint distributions satisfying the same distortion. And this minimum, I call it R of D, right? Well, now the R of di. So this is R of di is min of the mutual information over all possible p x I given x, such that expectation of d is less or equal than di. So this is like an obvious lower bound for every I. And here is where I use the convexity and the fact that the ray distortion is convex and non-increasing. Because first of all, I can multiply and divide by n, use Jensen's inequality. So I bring in this expected distortion over the symbols, mean distortion per symbol, and because of the convexity, I get a lower bound. So now this is precisely what we have defined as distortion between sequences, and we have assumed at the beginning that the code would achieve this average distortion over the sequences less or equal than d, and therefore when we plug in d, and because the function r is non-increasing, we get a lower bound. So at the end, when we put everything together, we conclude that if such code exists, then it must be nr, must be larger or equal than nr of d, where this is precisely that minimum mutual information that we have seen before. So we simplify, and then we conclude that if such code does exist, the rate must be greater or equal than that function that we have called rate distortion function, which is exactly this minimum of the mutual information. So this coincides, of course, with what we have found here in the achievability part, and therefore we conclude that the theorem is tight. Okay. So we can break here, and then in the last part we finish this chapter with a few more results.